Hello everyone, welcome back to heat transfer. This is Dr. Tian. Last class we talked about the difference between the subjects of heat transfer and thermodynamics. We know heat transfer extends the study of thermodynamics by studying the modes and the rate of heat transfer. Heat transfer has three modes: conduction, convection, and radiation. This class will briefly introduce the rate equation of each heat transfer mode. What is the unit of heat rate? We know whenever we encounter the term rate, it means something per unit time. The heat rate is energy transferred per unit time. So the SI unit of heat rate is joule per second, or watt. Now let's look at the rate equation for conduction, Free's law. Free's law is based on experimental observations instead of mathematical derivations, just like all the other first laws in nature. For example, the first law of thermodynamics was also deduced from experimental evidence. So now, question. What do you think Free's law should look like? Consider this wall of a building. Temperature T1 at the outer surface is higher than temperature T2 at the inner surface. What should the rate of conduction depend on? Of course, temperature difference matters. We know temperature difference is the drive for heat transfer. The larger the temperature difference is, the faster heat transfers. The size of the wall should matter. The larger the wall is, the more heat can be transferred per unit time. The thickness of the wall plays a role here. The thicker the wall is, the more time it takes for heat to be transferred from one side of the wall to the other side of the wall. What else? Yes, the material of the wall matters. Is the wall made of metal or wood? Well, of course, heat rate is gonna be different. Now we are ready to write Free's law. Here this K, we call it thermal conductivity. It represents how well this material transfers heat. So thermal conductivity is a property of the material. Each material has its own thermal conductivity. What is the unit of thermal conductivity? Let's see, thermal conductivity is negative Q over area over dt dx. So the unit is going to be the unit of heat transfer rate divided by the unit of area square meter. And dt dx is Kelvin per meter. So the unit of thermal conductivity is watt per meter per Kelvin. So now I'd like to emphasize another important thing. Sometimes from the textbook or from other resources, you do see the unit of thermal conductivity as expressed like this. So between watt per meter per Kelvin and watt per meter per degree Celsius, which one is correct? Think about this. Yes, both are correct. Why? This degree Celsius or Kelvin, apparently this is the unit of temperature, and this comes from here. dt represents temperature difference. Remember, the heat transfer rate is linearly proportional to temperature difference. When it comes to temperature difference, 1 degree Celsius is just equal to 1 Kelvin. So that is, if you want to raise the temperature of water by 1 degree Celsius or 1 Kelvin, it's exactly the same. Another question for you. What is this negative sign for? Do we really need it? Let's consider two cases. Case 1. Case 1, T1 is larger than T2. We know heat moves from higher temperature places to lower temperature places. So for this case, heat should move from left to the right. Let's define this as the positive x direction. So for this case, the direction of heat transfer is consistent with the direction of x. So we know our Q should be positive. How about now we use Fourier's law without a negative sign? There's dt dx. What is the sign of dt dx? This is a derivative. The sign of a derivative depends on how temperature changes with x. In this case, temperature decreases in the x direction. So dt dx should be negative. Over Q is positive, or dt dx is negative. So we do need this negative sign. Otherwise, it's not going to be consistent. Let's look at another case. T1, T2. In this case, T1 is smaller than T2. This is still our x direction. We know again heat moves from higher temperature places to lower temperature places. So heat should move from right to the left. So now the direction of heat transfer is opposite to the direction of x. So Q is smaller than 0. What about dt dx? For this case, temperature actually increases in the x direction. So dt dx is larger than 0. Now let's use Ka dt dx. Since dt dx is positive and we have this negative sign here, so we end up with negative Q, which is as expected. Now let's look at a quick application for Fourier's law. Let's consider this wall with assumptions: one-dimensional, steady conduction, constant thermal conductivity. What does one-dimensional mean? Well, of course, we only consider heat transfer in one dimension. In this case, we have temperature T1 on the left, we have temperature T2 on the right. It is different, of course, we have heat transfer in this direction. Then what about the other two dimensions? For example, this dimension. We just consider every point at this surface, at this fixed x, has the same temperature. So in this y direction, there's no temperature change. So there's no heat transfer in y direction. Similarly, in z direction. In z direction, every point we assume the temperature is the same. So there's no heat transfer rate in z direction either. So this is one-dimensional. Steady conduction. What does steady conduction mean? It means nothing changes with time. So heat rate, of course, it does not change with time. Temperature does not change with time either. Temperature could change with location, of course. Along the direction of the wall, temperature decreases, but it does not change with time. Constant thermal conductivity. Now, thermal conductivity could change with temperature. Along the wall, we have different temperatures. So theoretically speaking, thermal conductivity does change slightly, but it's very minimal. We ignore that change. So the question is, how does temperature change with x? Let's use Fourier's law. We know dt dx is temperature gradient mathematically. Physically, it represents how It represents the slope of temperature change. It gives us information how temperature changes with x, or how fast temperature changes with x. For this case, we know dt dx is negative q over Ka. We know for steady conduction, Q is a constant. K, we assume this constant. Area does not change, so this is actually a constant. What does a constant derivative means? That means temperature changes with x in a linear fashion. Then dt dx, since it's linear, we can just find any 2 points. Say t1 minus t2. Please note, at t1, the x, if at t1 x is 0, then at t2 x is going to be L. Or of course, we can use t2 minus t1. At t2, x is L, at t1, x is 0. So when you write derivative, be careful with this. So this has to be consistent. So this is t1 is at x is 0, t2 it is at x is L. Then we have Q. It's negative Ka t2 minus t1 over L, or Ka t1 minus t2 over L. Now I have a question about this area A. It should be the area of which surface? This wall has 3 surfaces. Should this be the area of this surface in blue? Or this surface? Or this one? Yes, it should be the area in blue. It should be the area which is perpendicular to the direction of heat transfer. Now I like to emphasize 3 terms. Heat, we use Q to represent it. It is the amount of thermal energy transferred over a time interval. So the unit of heat is the unit of energy, joule. Heat rate is energy per unit time, thermal energy transfer per unit time. We use Q dot to represent it. The unit is watt. What about heat flux? Heat flux is also a term we use very often throughout heat transfer 1. Heat flux, we often use little q dot to represent it. It is heat rate per unit area. So the unit of heat flux is watt per meter squared. Now let's look at quick example for Fourier's law. Say this is the wall of an industrial furnace. Temperature on both surfaces are provided. 1400, that's pretty high. This is a furnace. Dimension of the wall are all provided. Thermal conductivity of the wall is also provided. So let's try to find heat flux first. So heat flux is negative K dt dx. Negative K is 1.7. Note the unit of thermal conductivity. dt dx. So at x is 0, temperature is 1400. At x is 0.15 meters, temperature is 1150 Kelvin. So this is 2833 watt per meter squared. Then let's find heat rate. Remember, heat flux is heat rate per unit area. So heat rate is just heat flux multiplied by area. Which area should we multiply by? In Fourier's law, we multiply by the area of the surface, which is perpendicular to heat transfer direction. So we have temperature difference on this side, and this is the area which is perpendicular to heat transfer. Now let's look at convection. First, let's review the concept of velocity boundary layer. We know at y is 0, u is 0 due to viscous effect. We call it non-slip condition. At y is delta u, here delta u represents velocity boundary layer thickness. Velocity reaches 99% of the free stream velocity. Similarly, we can also envision the development of thermal boundary layer along a flat plate. So now we consider the flow of a fluid at a uniform temperature T infinity along a flat plate maintained at temperature Ts. So here we assume the fluid is colder than the wall. So on the surface, the fluid has the same temperature as the wall, Ts. In regions sufficiently far away from the surface, the flow temperature remains unaffected by the surface. So now let's look at the mechanism of convection. So at y is 0, since u is 0 due to non-slip condition, so that is there's no bulk motion at the surface. We can treat fluid there as stationary. We know heat transfer in a stationary medium is conduction. Actually, all the heat transferred between the surface and the fluid should be through this infinitesimal intersurface at y0. At y is larger than 0, velocity is not 0 anymore. So there is bulk motion of the fluid. So at y is larger than 0, heat exchange is due to the motion of the fluid. So we say convection is due to the superposition of conduction at the surface and the bulk motion of the fluid. We use the term advection to refer to the transport due to bulk fluid motion. And the term convection is customarily used when referring to this cumulative transport of conduction and heat transfer due to bulk motion. So based on the nature of the flow, we can classify convection into forced convection and free convection. It's about how fluid motion is induced. If fluid motion is driven by external device, such as a fan, a pump, or winds, that is forced convection. If fluid motion is simply set up by buoyancy, that is free convection. So this could be the circuit boards of your computer. You know they get hot. To cool it, in case A, we use a fan to drive the air to move through the circuit boards. This is forced convection. You know, otherwise air does not naturally move horizontally. So in case B, since these circuit boards are set up vertically, this fluid motion is simply driven by buoyancy. So this is free convection. Now let's look at the rate equation for convection. So convection in general is a very complicated matter. It is much more complicated than convection because convection heat transfer rate is affected by many factors. For example, the type of flow. Is it laminar, turbulent, or transitional? It depends on the geometry of the body. It's a flat plate, it's a cylindrical type. It depends on the physical properties of the fluid, the temperature difference between the surface and the fluid. It depends on the position along the surface of the body. However, the rate equation for convection looks really simple. It is called Newton's law of cooling. So convection heat transfer rate is linearly proportional to the temperature difference between the solid surface and the fluid. And this H, we call it convection coefficient. Actually, any study of convection ultimately reduces to a study of how to determine the value of convection coefficient. In chapter 6, 7, and 8, we'll focus on how to determine this convection coefficient. Prior to chapter 6, we'll use convection coefficient as a known value. Now let's look at radiation. The mechanism of radiation is energy transfer in the form of electromagnetic waves. Any matter at a non-zero temperature in Kelvin scale emits energy. So this covers all materials in engineering. Note, with radiation, there's energy outflow. There's also energy inflow. First, let's look at energy outflow, that is emission. So emission may occur from solid surfaces, liquids, and gases. Energy emitted due to its temperature is called thermal radiation. So thermal radiation leaving a body through its surfaces actually originates from the interior of the region. For example, the sun releases thermal energy, but it originates from the nuclear fusion in the sun. Surface emissive power, it is the rate at which energy is released per unit area. So you know the unit of surface emissive power should be the same as the unit of heat flux. The upper limit to the emissive power prescribed by Stefan-Boltzmann law. Emissive power, the upper limit. So this is sigma. This sigma is a small number. It's called Stefan-Boltzmann constant. Note, temperature here, it has to be in Kelvin. And what kind of objects can emit the upper limit of the emissive power following Stefan-Boltzmann law? It's called black body. The black body is not real, it's imaginary. So we imagine the black body has the largest ability to emit power. When you have a black body and real surfaces, the black body emits the highest amount of power, and that can be calculated using Stefan-Boltzmann law. So we use black body as a reference. Then what is the emission from a real surface? So you know this is the emissive power from black body. So here we have emissivity. So we use this emissivity to measure how close a real surface emissive power to black body. Then what is the emissivity of a black body? Of course, the emissivity of a black body is 1. And emissivity is in the range of 0 and 1. Besides energy outflow, there's also energy inflow. Here we use G to represent A radiation. It's the rate of radiations incident on a unit area of the surface. So the unit of A radiation is watt per meter squared. Among this incident radiation, some is absorbed, some is reflected, the rest is transmitted. So we use alpha to represent absorptivity. It is the fraction of G absorbed by the surface. We use rho to represent reflectivity. It's the fraction of G reflected by the surface. We use tau to represent transmissivity. It is the fraction of G transmitted by the surface. So now we have this relation. Alpha plus rho plus tau should be 1. Then how does each part affect the thermal energy of the surface? The absorbed energy, yes, it increases the thermal energy of the surface. The reflected part has no effect. The transmitted part has no effect either. And the emission reduces the thermal energy of the surface. So now we can apply energy balance on a surface. So we want to find out the net radiation from a surface. We need to consider both energy outflow and inflow. The energy outflow is emission. And part, we only need to consider the absorbed part. Consider the Earth and the Sun. Sunlight is thermal radiation generated by the hot plasma of the Sun. The Earth also emits thermal radiation, since the temperature of the Earth is also higher than 0 Kelvin, but at a much lower intensity because it is cooler. Remember, emission is linearly proportional to temperature to the power of 4. So the Earth, something of solar radiation followed by its outgoing are the two most important processes that determine the temperature and the climate of the Earth. So now we are looking for these two words. The Earth's absorption of solar radiation followed by its outgoing emission. So it's these two parts together determines the temperature of the Earth. So now let's look at black body again. The black body is an object that emits electromagnetic energy at the highest possible emissive power, governed by the Stefan-Boltzmann law. In the meantime, black body is also an object that absorbs all electromagnetic energy that falls onto it. So when it comes to emission, black body has the largest ability to emit energy. When it comes to absorption, black body can simply absorb all energy that is incident onto it. So there's no black body. Black body is not real. But in industry, we can often use a geometry like this to approximate a black body. So this is a larger box with a small hole. Assuming some energy flows into this box, part of the energy is absorbed here, the rest is reflected. Then some is absorbed here, the rest is reflected. So after many reflections and absorptions like this, all the radiation entering this cavity will be captured within the cavity, and none of them will escape. So that's why we can use a geometry like this to approximate a black body. So now let's look at a special and a very important case of a small surface exposed to large surroundings of uniform temperature. We're concerned about the net rate of radiation heat transfer from the surface. So the larger surface, this one, can be treated as a black body because all the energy leaving the smaller surface eventually will be incident onto this larger surroundings. So the emissive power from the larger surroundings can be treated by the Stefan-Boltzmann law. So TSURR represents the temperature of the larger surroundings. As for this smaller surface, we assume it's a gray surface. The gray surface is an assumption widely used in industry. So we assume that its emissivity is equal to its absorptivity. That is, the smaller surface has the same ability in absorbing and emitting energy. Then the emissive power from the smaller surface is, remember, emissivity multiplied by the highest amount of emissive power from a black body. Here, Ts represents the temperature of the smaller surface. Now we can apply energy balance onto this smaller surface. Remember, we need to consider both parts, the outgoing part and the incoming part. So it emits energy, so it loses energy. In the meantime, it also absorbs energy by absorption. The emitted part is epsilon sigma area Ts to the power of 4. The absorbed part, remember, the absorbed energy comes from the larger surroundings. And the larger surroundings emits energy at this rate. So the amount of energy that is incident onto the smaller surface is sigma times multiplied by T surroundings to the power of 4 multiplied by the area of the smaller surface. And then how much energy is absorbed among this incident energy? We multiply this by the absorptivity of the smaller surface. Remember, assume it's a gray surface, so its absorptivity is equal to its emissivity. So here we can take out emissivity. And sigma area of the smaller surface, Ts to the power of 4 minus T surroundings to the power of 4. So this is the net rate of radiation heat transfer from the surface. So besides radiation, now we have this smaller surface here. You note we also have gas between these two surfaces. And this gas is at a different temperature, T infinity. So you know there's also heat transfer between the solid surface and the gas by convection. How do we calculate convection rate? That is by Newton's law of cooling. That's H convection coefficient multiplied by area of the smaller surface multiplied by what? Remember, convection occurs between the surface and the gas. So this is the temperature difference between Ts and T infinity. So note, we have three temperatures here. We have Ts, we have T infinity, we have T surroundings. So in heat transfer 1, we assume and the gases do not participate in radiation. The radiation always occurs between surfaces. So when we calculate this radiation, it's between Ts and T surroundings. When we calculate convection, it's between Ts and T infinity. So the total amount of heat transfer from the smaller surface should be the summation between these two terms. So here is another question. Why do we feel chilled in the winter but comfortable in the summer when we have the same room temperature maintained by the heating or cooling system? This was one of the questions in the financial aid survey. Many students answered it was a mental thing. Is it?